An operation that we will frequently be interested in is called orthogonal decomposition. And along with that is this notion of vector projection. Here I have two non-zero vectors, u and v. The angle between them in my picture looks to be like an acute angle. They're not orthogonal to one another. What I would like to do is take that vector v in the picture and I would like to project it down onto the vector u. And I want you to imagine the shadow that's cast by v onto the vector u. And I'm going to call that vector u parallel. I'm using two lines there to represent that it's parallel to u. In words, what I'm doing is I'm projecting v onto u. So u parallel here is the projection of v onto u. I can also do this in the orthogonal direction. So I want you to imagine this vector that I've drawn here in orthogonal to the vector u, and I want you to imagine kind of the height of that being determined by v. So I want you to kind of imagine casting a shadow of v into that orthogonal direction, and we're going to get a vector I'm calling u perpendicular or u orthogonal. And if you look at the picture and use the parallelogram law, you see that these two vectors, this orthogonal vector to u, that they sum up to v. So this plus this form a rectangle now, not even just a parallelogram, and the diagonal of that is v itself. So we're decomposing v into two orthogonal vectors, into u parallel and u perpendicular. They are at a right angle to each other, and their sum is my vector v. This is useful in applications. So for example, you might have an object moving in the direction that u determines, but the acceleration is in the direction of v, and you'd like to know how much of that acceleration is in the direction of motion versus the direction orthogonal to motion. So let's see if we can figure out a formula for u parallel. We're going to focus on this one. So what is u parallel? And a vector is direction and magnitude. So if you want to answer that question, answer both of those questions independently. What is the direction of u parallel? And the direction of u parallel is the same as the direction of the vector u because they point in the same direction. So u parallel is the direction of u. What we're going to do is find the length of u and normalize and get a unit vector. So remember that when we say the direction of a vector, we mean the normalized vector that vector determines. So we're going to take u over the length of u. The next thing that we need to figure out is the magnitude or the length of u parallel. So this blue length here. What is that quantity? Well, we're going to use some trigonometry here. There's a right triangle that u parallel form. V is the hypotenuse of. Here's the right angle. And the angle between those two vectors is going to be critical here. I'm going to label that theta. And we're going to use a little bit of trigonometry in that right triangle. This side length is the adjacent side to theta. So we should have some relationship involving the cosine of the angle between them. So the length of u parallel is going to be the hypotenuse times the cosine of the angle between them. Length of u parallel is length of v times cosine of theta. If you prefer, cosine of theta is the length of u parallel, that's the adjacent side, divided by the length of v, that's the hypotenuse. Cosine is adjacent over hypotenuse. I'm solving this for the quantity that I want, which is the length of u parallel. We're now going to play a little algebraic trick here by multiplying by the length of u over the length of u. That's not part of this expression. I'm just multiplying by 1, and then I have the original expression, length of v times cosine of theta. So I haven't changed it by doing this, and why would I do that? Well, I have length of u, length of v times cosine. That is the dot product of u and v. So the length of u parallel is the dot product of u and v over the length of u. So let's put it together now. U parallel has length given by this dot product expression we just derived above, and then I'm going to multiply it by this vector, this unit vector here, to get a vector, this blue vector here. So we're taking this unit vector and we're scaling it by the length that we just found that the blue vector should have, and that should get me my blue vector. So u parallel is the dot product, and notice I have a square of the lengths in the denominator, so I've written it as length of u squared, and then I'm scaling the vector u by that amount. This is a complicated expression. There's a lot going on in here. All the numbers in the front, all of that are scalars. U dot v is a scalar, length of u squared is a scalar. So this is a number in front, and then I've got my vector part here, u. We're scaling u by this amount to get the blue vector. U parallel then, just summarizing, can be written even more nicely. The squared length of a vector is the dot product of the vector with itself. So squared length of u is u dot u. So the way to find it is we take u dot v, we take u dot u, and we scale u by that amount. That will get the parallel vector. If I want the orthogonal vector, all I need to do is solve for it in this equation. V is the sum of those, so u orthogonal will be the difference, v minus v parallel. These two vectors will sum up to v, and these two vectors are orthogonal to one another.